Hey guys, welcome back. Today we'll be finishing up chapter 6. We'll be discussing re-expressing data. So whenever we graph out our scatter plot and if we have curved data, what can we do in order to re-express that data to make it linear so that we can actually calculate a correlation coefficient like what we want to do with the measuring the strength of a linear association, like with the correlation table that we talked about yesterday. So a good example of when we would have data that needs to be re-expressed is actually from photography. So here we're looking at shutter speed versus f-stop. Now f-stop is actually the measurement of it's the width of the aperture, so basically how much light's being let in. So here you can see we have we're just letting in more light. And then over here with the shutter speed, so this is a shutter speed of 1/60th. It's measurement of a frequency, right? So that means that the shutter would open and close 60 times a second, or every 1/60th of a second. And as we increase our shutter speed, we notice that there's less and less light coming through, and the exposure in the photos is getting worse, right? There's not as much exposure, so not enough light can come in, so we can't get all the detail, and the images look really dark, even though all these photos were taken at the same time. So anyway, if you know anything about photography, it's all about it's about matching. If you have like stills or movement, you can't have as much exposure in fast pace like sports activities and stuff like that. You have to have a really high shutter speed. But if you got a really high shutter speed, that also means you have to let in a lot of light. You can have slow or long exposures if you're dealing with still photography, and you can deal with really small amounts there. If you have a small shutter speed, it'll be okay. Or like a what would you call that? A time lapse, kind of the same thing going on there too. Anyway, so here's our data. We have our shutter speeds, and these are the frequencies written here. And then we have our f-stop, which is, I don't know quite how f-stops are calculated. You can look it up if you want. I don't really do photography. But anyway, enter the shutter speed in list 1 and the f-stop in list 2. So if we'll get out your calculator, I've already put mine in just for the sake of saving time. I do want to show you how you put it in though. If we just put 1 divided by 1000, we put it in for list 1, we hit enter, it'll go ahead and convert that to a decimal for you, and it'll give you all the precision that it can handle in the calculator, which is actually really nice. And then our f-stops, we'll put those in list 2. And then the first thing we always do is graph it out. Before we calculate a linear regression to find the correlation coefficient, we always graph it out to make sure that it's appropriate, the graph that we're dealing with. So that's going to be list 1, and which is our shutter speed, and list 2 for our f-stop, which has to do with our aperture size, then zoom 9. And we graph it out like you see here. It's going to be curved. So we'll talk about why it's curved, but it is curved. So at this point, it would not really be appropriate to calculate a correlation coefficient, but let's go ahead and do it anyway just to prove a point. So if we go to stat, calculate linear regression, which is the 4th option, we're going to go between list 1 and list 2. We're not going to store the regression equation. We'll do that later. We'll actually do regression equations and linear regression. If you're in AP Stats, we'll start that tomorrow on Wednesday. If you're in on-level stats, I'm not going to give you guys assignments on Wednesdays anymore. So you'll just do that assignment on Thursday, and you'll be a day behind each week going forward. All right. So anyway, we've got that. We have a correlation of 0.979 if we round. So if we look at that correlation coefficient, that's actually really strong. We would say that's a very strong association. But because it's curved, that's not actually a good measurement of the strength, and the strength of the association is actually going to be even stronger than that whenever we re-express the data. So how do we re-express the data? Well, okay, we'll do the questions from the homework first. All right, is it appropriate to calculate the correlation coefficient? So first of all, are we dealing with quantitative data? Yes, we do have quantitative data. I need to fix those. Both of them are quantitative with their units, so no big deal. On the second part is it linear? Okay, well, it's not linear, so it's not really appropriate to calculate the correlation coefficient, but we did it anyway. And then outliers, we clearly don't have any outliers. It's all following within the pattern. Nothing's really deviating very far from it. All right, so now let's re-express our data in order to straighten it up by squaring the f-stop. So if we look back at our data here, you might notice that these values here they're kind of following like a square root curve. So if we square our response variable, the f-stop here, what that's going to do is the values that are close are still going to be close, and the values that are even higher are going to be pushed even higher, right? Because when you square something, the bigger values get even bigger, and the smaller values don't change as much as the bigger ones do. So what we're doing is we're kind of taking all these high values and we're increasing them drastically to try to straighten it back out, and all the values that are small are not going to be impacted that much. Okay, so anyway, that's kind of what's going on, and that's our logic behind why we're going to square the response variable. So we're going to take our L2, our list2, and we're going to square it. So in the calculator, we can go to stat, edit, totally fine. And right here for list3, we can define list3. It's one way of doing it, or you can store it, but I like defining it. It's actually really nice. Once I learned this trick at the AP Summer Institute. Sorry. Okay, so what we're going to do is we're going to do list2. So list3 is defined as list2 squared. Okay, and then just hit enter. And what it's going to do is it's going to take all of our f stops and they're going to square them. So 4 squared 16, 8 squared 64, 121. So that's exactly what we expect, right? So now let's graph it again, but this time we're going to use the re-expressed response variable, which would be list3. Okay, then hit zoom 9 again, and when we do that, bam, just like that, it's going to be straightened out, which is really, really cool. Okay, so you see the original, and then we see the straightened out one. And also notice in the graph here, when we re-express that data, we show that we re-expressed it by putting the f-stop squared. So we're telling exactly how we re-express the data by in our labeling of our axes, and the shutter speed stay the same. Typically, we will re-express the response variable, and we don't touch the explanatory variable. But in the attack of the logs, I think it's anyway, in the attack of the logs, we'll discuss, sometimes we do re-express the explanatory variable as well, usually with logarithms, but we'll get into that later, specifically next chapter. All right, so does the re-expressed data now meet the conditions for calculate correlation coefficient? Yes, because it's linear. That was the big issue we had over here, is that it wasn't linear. If I draw the point from the smallest point to the largest point, you can see how it's clearly curved and deviating from that. In this case, it's not, so we're good. Calculate the new correlation coefficient, so no big deal. So go to stat, calculate the fourth option for linear regression. We're going to do list 1 to list 3 this time, because list 3 is our re-expressed data. And then hit calculate, and now it's almost 1, right? So 0.998, where it used to be 0.979. So it didn't increase that much. Both of those are very, very strong. This one's nearly a perfect correlation, right? And actually the only issues that we have here, because what we're actually measuring is a natural phenomenon, kind of like gravity, okay? So there's a natural law going on here with the amount of light that we let in and the amount of time that we let the light come in. And that, what we're measuring here, the only reason that this is not exactly 1 is because of the rounding error that was involved in rounding off the f-stops. And if we use their actual full precision, then we would have had, they would have been 1, which is actually really, really cool. All right, so re-express it. We did calculate correlation. Okay, how did the calculate correlation coefficient change by re-expressing? It went up as we expected it would, but the real problem is that this was never an appropriate measurement of the strength of the association, because the association was curved. And so now the correlation coefficient, because it was linear, this is a proper measurement of the strength of the association, because it's a linear association now. All right, so why did we square the f-stop? So what's going on is we're letting in the same amount of light to get the proper exposure to get the right amount of color. So this is their recommended, these are what it shows as, those were the recommended f-stops for a certain shutter speed, depending on what kind of action film you're filming, right? All right, so in a certain amount of time, we need to let in the same amount of light, regardless of how much our f-stop is, so what our aperture size is, in other words. Now time is like a one-dimensional unit, where the f-stop is, we're dealing with area, which is like two-dimensional, so like a one-dimensional length of time. So like if we cut the time in half, you can imagine how that would affect it. But the area, if we cut the area in half, or the side links in half, it'd actually take the area by a fourth, etc. So we're dealing with 1 dimension to 2 dimensions. And so f-stops, I believe, are actually kind of measuring like the diameter or the radius or something. I'm not sure exactly. And so if you want to go from a diameter to the actual area, what you would have to do is you'd have to square the f-stop, and that's what we were doing. So we were going from really a one-dimensional length of an f-stop to a two-dimensional length to get the area, because what we're really trying to do is have in the same amount of length of time, we want to have the right amount of area to let the right amount of light in, if that makes sense. Hopefully it does. Anyway, so kind of cool. They don't always have really nice, elegant solutions for why we re-express with certain things like squaring or taking the square root or logarithms or something. But sometimes if you just think about how the data is the variables we're using, you might be able to think through it. All right, so that was it. Just 10 minutes, not too bad. And a really important topic. We will do a lot of re-expression of our data, especially in the next chapter. All right, so 38, drug abuse. A survey was conducted in the United States and 10 countries in Western Europe to determine the percentage of teenagers who would use marijuana and other drugs. The results are summarized in the table. So we want to go ahead and put all of that data into our calculator. All right, so what we're going to do is go into stat and then to edit. And I'm going to go ahead and put this in, we'll put it in list 3 and list 4. That's fine. So I'm going to pause the video and then I'll come back when I have all this in, because otherwise this will be really boring. All right, so we have all of our data in here. We can make sure that our lists are the same length so that we didn't have a typo. You also might scan through the data real quick just to make sure you don't see any glaring errors like we missed a digit or something like that. So it looks good to me. So we're going from list 3 to list 4. So we want to see, the question is, what's the correlation between the percent of teens who have used marijuana and the percent who have used other drugs? So the question we have is what's going to be in the x-axis and what's going to be along the y-axis. So I think the question they were going to be asking, if we look down in part D, is do the results confirm that marijuana is a gateway drug? That is, that marijuana leads to the use of other drugs. So what we're trying to see is, do nations, at least in Western Europe and the U.S., do they nations that have higher marijuana use, do they also have higher drug use, other drug use? And so we're going to put the marijuana use on the x-axis and other drugs on the y-axis. So that would mean our list 3 is our x-axis and our list 4 is our y-axis. Usually we like to put them in order like that, 3 and 4, but also another thing is if you calculate the correlation from x to y or from y to x and you switch the order, you'll get the exact same correlation. So that's not really that important, but it does change when you do a linear regression. But we'll talk about that tomorrow or on Thursday if I see you then. So we're going to go to stat and calculate a linear regression. That was not what I was trying to do. Let's try that again. So stat, calculate, fourth option, linear regression. We're going to go from 3 to 4. All right, I'm not going to store the regression EQ because we don't need that yet, but we will do that next. All right, so it's 0.93. So that's a really strong, it's a really strong association, and that's what it would look like if we graphed it out, which again, you just go do your scatter plot. List 3 would be your x-axis, list 4 would be your y-axis here. So it looks like in countries, as the percent of teenagers who are using marijuana, the other drug use is also going up as well. Okay, so write a brief description. Okay, we already said the correlation there. Right, brief description of the association. So this is, we want to talk about direction, strength, and form. So the direction is positive, it looks linear, and it looks to be a moderately strong association, or just a strong association because of the correlation coefficient. Or do these results confirm that marijuana is a gateway drug? That is, that marijuana use leads to the use of other drugs. So the problem we have there is with correlation does not equal causation. So just because there's a strong association between the use of marijuana and other drugs does not mean that marijuana is causing the other high use there. So there could be other lurking variables. I don't know what those might be. We also don't know. It just could be the other direction as well. So perhaps people are using other drugs and that leads them to use marijuana. I have no idea. So without a carefully designed experiment, we can't make conclusions that have anything to do with causal relationships unless we have carefully designed experiment with randomization, which of course we're going to talk about that unit in gathering data, which will be the next unit we talk about because it's really important to statistics. All right. So let's move on. So yeah, just like when we talked correlation, causation, this was the number of storks in the human population in that town. There's a lurking variable, and actually the roles were reversed. So as there were more chimneys, there were more storks. They had more places to nest. All right, 48 flights in 2010. Here are a number of domestic flights in thousands flown each year from 2000 to 2010. And that's where they got the data. So we're going to put this in list, I think I'm going to do it in list 4 and list 5, or list 5 and list 6. I think I've already put them in there. Yeah, I did. All right, so when we're talking about years from 2000, 2010, instead of writing 2000, 2001, 2002, they're doing years since 2000, and so they're subtracting 2000 from it, just shifting, in other words. So 0 all the way through 10 is how we're going to put it in the calculator. This is actually really common to do that. Even if we started, like, let's say 1970, we would do years since 1970, and then 1971 would just be listed as 1, et cetera, et cetera. All right, so then list 6, you got to put in all that data. It shouldn't take you too long, but do not rush it, because if you mess up some of the data, it'll throw off your numbers. But anyway, so that's our data. The first thing we want to do is visualize it. So we're going to do a scatter plot. We're going to go from list 5 to list 6. Alrighty, and then zoom 9. Whoa. All right, so that was not very pretty. I think I can, yeah, there we go. Click and drag it from here. All right, so find the correlation between, okay, wait, timeout. Is this appropriate to find the correlation? No. Why? And that's why they were talking about that in part C, because it's not linear in the first place, right? So if we're trying to fit this with the linear model, it's not going to work, okay? All right, so find the correlation between flights in the year. We can do that, but again, it's not really measuring the strength of the association because it measures the strength of a linear association. So this is going to be a much smaller value than what we would expect. That's a pretty strong association. That looks more like, I don't know, like 0.9 or 0.95, but we're probably going to get something, I don't know if I had to guess, maybe like 0.4, 0.5 or something like that. All right, so we'll see what it is. I honestly don't know. All right, so second 5, second 6. There we go. Okay, then hit calculate. Oh, nice. Right between 4 and 5. Exactly. Well, did I say 4 and 5 or 5 or 6? I don't know. Doesn't even matter. But yeah, it was pretty weak if we looked at that. But this is actually a much stronger association and just needs to be re-expressed if possible. And actually, it's not really possible for us to re-express data that's parabolic like that. Yeah, so kind of cool to know. All right, make a scatter plot, describe the trend. So you could say this is like an inverse parabola. That would be one way of doing it. Another thing is you could describe it as trends. So looks like, oh yeah, so what was really happening is that there was something special that happened around 2001 with aviation in the United States. Do you remember what happened? You probably weren't born yet. 9/11 happened, right? So right after 9/11 and the Patriot Act and stuff like that, and then TSA and all that fun stuff, people stopped flying for a while. They were scared, right? Kind of like we're scared right now. But then things kind of went back to normal. I didn't mean to make a political statement, but hey, we're going back to school. It's gonna be great. Can't wait. Oh, the other thing, because now that I'm making political statements, we'll go back to this. All the people I know who smoke marijuana are losers. I wonder if I'm going to keep that in the video. I'm just saying. I'm not saying. I'm just saying. That's just my anecdotal evidence. All the people I knew in school that smoked weed, they were losers. That felt so good to say. Anyway, I mean, when I go back for my 10-year reunion and they're like touring the campus at PCO, because where I graduated from or whatever, I'll be like, yeah, look guys, I got real estate. Like, wow, you're such a loser. Hey, it took me 8 years, but I'm finally popular in high school. So wrap your head around that one. I'll see you guys.